Welcome. On this video, we're going to be discussing how do we solve exponential equations. So let's get started. Let's start by looking at this small introduction question which states, let's find a value of x that will make the following statements true. So looking at example A, note that this is an example of an exponential equation. The reason why we call it an exponential equation is because notice that the variable that we're looking for, it's on the exponent, and there's an equal sign involved in it. So that's an exponential equation. Now, there are different ways that we can solve exponential equations. The first way is just to look at the statement and see which statement will make sense. So looking at A, we have 2 to the x equals 32. So now, what value of x will make this statement true? So 2 to the what exponent, it's equivalent to 32. Well, in this case, x is 5. Because notice that 2 to the 5th is equal to 32. Now, we can approach the same problem in a different format. So let me just rewrite the same problem here. And now, the first method is what we call just plug and verify. We plug it in, we verify that it's true. But if you want a more algebraic way, we can do what is called the same base formula. So notice that on the left-hand side, we have a base of 2, which is raised to the x. So now we want to ask ourselves, well, is it possible for me to represent the value of 32 as an exponent whose base is 2? Well, notice that, yes, because 32 is equivalent to 2 to the 5th. And now that we have the same base on the left and the same base on the right, they will cancel each other out. And now we can say that x is equivalent to 5. Now this method, this is the second method. The second method that we discuss here is what we call the same base. So as long as they have the same base on the left and the same base on the right, they're going to cancel each other out and the exponents are going to be equal to each other. Let's try to do the same for example B. Notice that for example B, 10 to the x, well, the first way, we could just plug in a value and notice that in this case, x will be equivalent to 3, since 10 to the third is equivalent to 1000, so that checks out. Now the second way, same idea. Notice that on the left, I have a base of 10. So now I want to ask myself this question, is it possible for me to represent 1000 having a base of 10? Well, notice that we could express that as 10 to the third. And now that they have the same base, they cancel each other out. And now my result is that x is equivalent to 3. Notice that we got the same result. For example C, notice that there's not much to think about it because they already have the same base. So in this case, the bases will cancel out. So they have the same base, they can cancel each other out. Now I'm going to make the exponents equal to each other. So 3n equals 3n. And now notice that the left-hand side, it's always going to be equivalent to the right-hand side. So in this case, n can be any value. So we can say that we have infinite solutions. It doesn't really matter what value of n that we plug in, because whatever value we plug in on the left, it's going to be the same value we plug in on the right. And they'll have 3 on both sides, the same expression, it's always equivalent to itself, regardless of what value n takes. So what we have discussed so far are 2 different methods that we can use to solve exponential equations. So let's just summarize what we just did here. So based on our observations in the introduction questions, let's write down a rule for solving exponential equations. So what we have done here is that if the base of the exponential equations are equal, then they cancel out. And I think I should say here the bases, because it should be plural. Oh, that's a very ugly S. So the bases. So what I'm trying to say here is that if the base on the left is equal to the right, then they cancel each other out, and we just let the exponents be equal to each other. But we might encounter situations of this form. Because now we want to solve This is still an exponential equation. So notice that the variable's on the exponent, and we still have an equal sign. But now it's not as straightforward as before, because now if we want to use the same base formula, notice that 72, is it possible for me to write down e to some exponent equals to 72? Well, remember that e is the Euler number. Euler, I should say it. So is it possible for me to write down the Euler number times some exponent is equivalent to 72? It's not as straightforward as the examples that we do have in our previous examples. So how do we approach problems of this form? Well, when we are not able to properly use the same base formula, what we do is we use either our logarithms and natural logarithms. Because remember that the logarithm, it has a base 10, and the natural logarithm has a base of e. So the way that we want to tackle this type of problems is the following. Well, notice that I want to solve for x. In some way, I kind of want to get rid of this e. But I know that ln has a base of e. And remember that we do have this property where if the base is equivalent to what's inside the parentheses, they cancel each other out. And that's exactly what we're going to be using here. So if we take a look at example A, what if I take the ln on both sides? So what if I write down ln of e to the x equals ln of 72? Well, remember that ln has a base of e. And by doing this, the ln will cancel out with the e. And now we're just going to have the variable that we're looking for. So now x is equivalent to ln of 72. And now this expression, the natural logarithm of 72, is something that we can use a graphing calculator. So what exactly is this value? Well, we got a graphing calculator. Notice that ln, it's right here. So we're going to type in ln of 72, close parenthesis, and that's going to be equivalent to 4.27. So that's exactly what x is equivalent to. X is equivalent to 4.27. So now notice that there are times where perhaps the same base formula is not going to work out because it's just going to be hard for us to represent one number using a different base. And whenever we have those situations, then it is important for us to know that we still can use logs or ln regarding of the situation. Now, are we always going to be using ln? Not always. But if the base that you want to get rid of, it's of an e, of an Euler number, then it is just beneficial for us to use ln. For others, where perhaps our bases are just regular numbers, I just recommend for you to use log. But let's take a look at example B now. Example B. So how do we tackle problems where perhaps we have multiple things going on? Well, notice that before we took the ln to both sides, we wanted to make sure that the expression that has the variable that we're looking for, it's isolated, which in this case it is not. Notice that 2 to the x is not isolated. So the first thing we want to do is just isolate the expression. So to do that, let me just divide it by 3. So now we're going to have 2x equals, so this is going to be a decimal. Let me just keep it as a fraction, 42 over 3. But what's important here is that now we have the expression isolated. So now that we have the expression that is isolated, what we can do here is, let's take either the ln or the log to both sides. But in this case, since the base is a number, I'm just going to take the log instead of taking the ln. So I'm going to take the log on the left. So the log of 2x equals the log of 42 over 3. Now let's pause here for a second. Remember that for log, the base is 10. So if the base is 10 and the base of the expression is 2, they don't cancel out. But why do we still want to take the log? Because we can still use the properties of logs. And the property of log says that if you have an expression, what we can do to the exponent is that we can bring this exponent to the front. And now this expression just becomes x times the log of 2 equals the log of 42 over 3. And when we bring the exponent to the front, it becomes a multiplication. And this is still our objective. Our objective is to still solve for x. So how do we solve for x? Well, they are multiplying, so let me just divide. So let me do the opposite. So let me divide by log on 2 to both sides. Now, log of 2, it's a number. Let me see what the value is. So the log of 2, that's equivalent to 0.3. So just imagine that you have x times 0.3. So I can divide it by a number. It doesn't really matter. It's just a number that looks, very fancy because it has the word log in front of it. So now that we have this, I have an expression for x. So now I know that x is equivalent to the log of 42 over 3 over the log of 2. So what exactly is this expression? Well, let's find out. So the log of 42 divided by 3, and I'm going to divide that by the log of 2. Let me close my parentheses. And now this is equivalent to 3.8. So now I have that x is equivalent to 3.8. And notice that what we just did here, we just used the properties of logs. I know that if I have an expression which has an exponent inside the log, I can just bring the exponent to the front. And I just took advantage of that. For example C, notice that it just doesn't look as straightforward, but the idea is still the same. This is my objective. My objective is to solve for x. X is part of this expression, e to the 2x. So let me just try to isolate this expression. Let me try to eliminate everything besides this expression. I want to just isolate this. So how do I do that? Well, first, let me get rid of that 3. So if I add 3 to both sides, let me just separate my work here. I'm going to have 4 e to the 2x. That's still equivalent to 5. What I want to do here, I want to just isolate this expression. So let me divide it by 4 now. So if I divide it by 4, that's gone. So e to the 2x is equivalent to 5 over 4. And at this point, we have the expression isolated. So now we can either use the log or ln. Which one do we want to use? In this case, I am going to use ln because I can see that my base is e. So if I take the ln to both sides, so now if I take the ln of the left, and if I take the ln of the right, notice that my base is e, this is going to cancel out, and now I have 2x equals ln of 5 over 4. My objective is still the same. I still want to get rid of, I just want to isolate this x. So let me do that by eliminating the 2. Note that the 2 is in front of the variable, so that's multiplication. So let me do the opposite, which is division. So that cancels out. And I have an expression. So now I have that x is equivalent to ln of 5 over 4, and the whole expression is divided by 2. So what exactly is this? Let's find out. Let me clear this. So let me take the ln of 5 divided by 4, and I'm going to divide that by 2. And that's equivalent to about 0.11. So the main idea here is that we got 3 ways to solve exponential equations. The first one is just to look at the expression and see if you can just figure out the value. The second way that we can solve exponential equations is we can see if we can write down the left and the right using the same base. We call the same base formula. So they have the same base, they cancel each other out, and we got our result. Now the last way is to either use the properties of logs or use the properties of ln. And this is never going to fail, but we usually just reserve this for whenever we have expressions that are a little bit more complicated. So we're going to take a look at this last example now. But before we do that, let's just fill in this box, which is based on the problems from the previous example. What technique can we use to solve exponential equations? Well, we can use the properties of logs. Or natural logs to properly solve for those exponential equations. So example 2, it looks a little bit complicated, but let's just try to break it down. So the objective is still the same. I want to solve for this variable t. So how do we do that? First, let me isolate the whole expression. So how do I isolate the whole expression? First, I need to get rid of that 4. So I'm going to add 4 to both sides. And now I'm going to end up with 2, still parentheses, 2t minus 5 equals, that's 15. Notice that this is multiplying. Let me get rid of that 2 now. So let me divide it by 2. So 2t minus 5 equals, that's still a fraction, so let me just keep it as a fraction. So we have achieved our objective. Our objective is just to isolate the expression which has the exponent that we're looking for. So now that we have this, let me take the log to both sides. So I'm going to take the log of the left, and I'm going to take the log of the right. And by doing this, what we have accomplished is that this whole big exponent right here, 2t minus 5, is going to come to the front. And when we push it to the front, it becomes multiplication. So now we have 2t minus 5 times the log of 3. That's equivalent to the log of 15 over 2. My objective is still right here. So I wanted to solve for t. So let me get rid of this log of 3. Notice that it's been multiplied. So I'm just going to do the opposite, which in this case is division. So let me divide the log of 3 to both sides. So now that I have this, now this becomes 2t minus 5 equals the log of 15 over 2 all over the log of 3. And once you have reached this point, you have two options. Either we can compute what the log, the whole right expression is. Well, let me actually compute that. So I can do the log of 15 divided by 2 divided by the log of 3. So the right-hand side, I can just write it out as 1.8. But notice that by doing that, I'm going to ignore all these decimals that are on the right-hand side following by the 8. So I don't suggest for you to just compute what this expression is and just work with the decimal. I will prefer for you to just keep working with this expression because we're going to get an exact expression for t. So instead of just finding out what this expression is and just work out with the decimal, we're just going to continue working with the expression. So continuing with the expression, I still want to solve for this t. So imagine this is just a number, and let's just treat it as a number. So what do we do now? Well, let me add 5. So I'm going to add 5 to both sides. So I'm going to get 2t equals still. I'm just going to work with this expression instead of just converting it into a decimal. So this is 2 plus 5. And now what I want to do is I want to get rid of the 2. So I'm going to divide it by 2. And I need to divide the whole expression by 2. So now I have this huge expression for t. The log of 15 over 2 all over the log of 3 plus 5. This is my numerator. So this whole expression is my numerator. And I'm going to divide that all by 2. So let's just do that real quick. Let me just compute the numerator. So let's just do that. I'm going to get the log of 15 divided by 2. And that I'm going to divide it by, and that I'm going to divide it by the log of 3. Enter, I'm going to add a 5 to it. And then that is what I'm going to divide it by 2. Because this is my numerator, so my numerator needs to be divided by 2. And now I have an expression, 3.41. Oh, let me just do 42. Let's just round it. Even though the last example was a little bit more complicated, notice that we didn't do anything new here. All we did was just isolate the expression. Once that is isolated, let me either take the log or ln to both sides. By doing that, I bring the exponent to the front. And then I just did some algebra to it until I get my final result. And with this, it concludes our lesson for solving exponential equations.